Hi, my name is Romain, and I'm a fifth-year PhD student at Victor Kunchev's lab at EPFL. So today I'm going to talk about some projects I worked on during my PhD, and I worked on many projects. So let's focus only on two of them, namely a parsing algorithm project and a deep learning project. Let's focus on this one first. And in this project, we are trying to prove two program equivalent. How do we do this? Well, one way is to find a path of equivalence preserving transformations between the first program and the second program. So if we can find such a path, we know for sure that the two programs are equivalent. Finding such a path, however, is not an easy task, as the search space can be huge, and exhaustive search techniques can take too long or are not practical at all. So in this project, we focused on the simpler setting where our expressions are arithmetic expressions composed of variables and addition and multiplication. The type of transformations we had were distributivity and commutativity and also associativity. So here in this case, we can see that there exists a path between the first and the second expression by using distributivity first and then applying commutativity 3 times different places in the expression. So this is not the only path. There exists another path that is shorter. So for instance, if we apply commutativity twice and then distributivity, we get a shorter path to the target expression. And we are interested in short paths, so this one is better. So now we try to use deep learning to guide the search towards simple and short paths by estimating distances between expressions. So how do we do this? Well, we first convert the two strings of characters into parse trees, and then we feed them into a graph neural network that gets embeddings for the two expressions as vectors. When we have those vectors, we simply take the Manhattan distance between the two, and we use this as an estimation of the distance between the two expressions. So how do we use this information? Well, first we say, well, the distance between the source and the target is 3.04 here. And if we apply distributivity, we feed then this expression and the target into the network, and we get the distance of 3.09. So we haven't improved the situation. So let's try some other transformation first. For instance, commutativity. And here we see that the situation improved because the distance is shorter, and so on, up until we get to the target. So compared to an exhaustive search, such as breadth-first search, this has many advantages, such as it greatly reduces the number of visited states, and it is much faster on complicated instances where expressions are far apart. There are many challenges ahead, and the first one is to scale this technique to more complex expressions. So we only considered arithmetic expressions in this work, but we would like to scale it to expressions in programming languages, for instance. And we also would like to find an efficient way to train such networks, because while training data is hard to find for such problems, and maybe techniques such as reinforcement learning might be needed. What we've done is available online on GitHub. The second project I want to talk about is this parsing algorithm project. And this project started early last year, and I set myself the goal to improve the life of students in a compiler construction course. So I TA'd the semester before in this course, and I noticed that some students struggled with one part of the compiler project, and I said to myself, well, let's try to improve the situation. So they were assigned a compiler project for this semester, and they had to build these compilers that takes as input Scala files and has to output WebAssembly programs. So as usual, the compiler is decomposed into several phases: a lexer phase, a parser phase, and at the very end, you have a code generation phase. So the problem they had was mainly in this parser phase. So the goal of a parser is to turn a sequence of tokens into a structured value, such as an abstract syntax tree. And the way they used to have to do this is to write a grammar, and then an algorithm would take this grammar, this sequence of tokens, and produce a parsed tree. Now, this parsed tree was not the abstract syntax tree that they were after, but just an intermediate representation. So they had to use another phase called the tree converter phase, where they fed this parsed tree, and then they had to obtain the final abstract syntax tree from this. So this phase was particularly painful, and therefore I set myself the goal to eliminate it completely and keep this view of parser as a simple one-phase conversion between token sequences and values, so abstract syntax trees. And the way we do this is using parser combinators. So I set myself the goal to use parser combinators for this project. And the idea of parser combinators is very simple. So you have basic building blocks from which that you can combine to obtain more complex parsers. So the building blocks that we have, for instance, are simple LM parsers, which simply take a single token and produce the token itself as a value. We can compose simple parsers by using disjunction, which would behave either as the left parser or the right parser. We can also compose parser in sequence, so taking first querying this parser, and then with the rest of input querying the second parser. We can also apply functions on the parse values. So for instance, we can use this combinator here to change this pink value into an orange value. So now that we have a way to describe the parser, how do we actually parse? And the usual answer with parser combinators is to use a recursive descent. But we didn't want to use this technique because, well, it can be slow and it's also very far from what is taught during the course. So we said, well, let's try to find something else. So what was taught in the course was LL1 parsing. And the way it's usually done is to take your description of the parser and turn it into an automaton. And as I'm terribly lazy, I didn't want to do this transformation, and also it's very error prone. So I said, well, let's try to stay at the level of parsers as trees. And one technique that works directly on trees is called parsing with derivatives. And the idea is very simple. It is to introduce this operation called the derivation, which represents the state of the parser after processing a single token T. So if we have this parser S here that accepts this token sequence that starts with a T, if we derive it with respect to this first token, then the parser is going to be equivalent for all the postfixes of the input tokens, and it's going to produce the same value. So once we have such an operation, it's easy to devise a parsing algorithm by simply invoking derivation up until the input is completely consumed, and then you just query for the value associated to the empty string by the parser, which is a much simpler operation. So if we look at what's going on under the hood, we can see that each time we derive, the parser state, so the representation of the parser can grow. And this, in practice, can be a problem because, well, it's terribly inefficient. The way we do derivation is that we start from the root of the tree, and then we have to go down each level that we've added towards the leaf where the interesting part happens. So I told myself, what if we reverse some of the arrows on the path from the top to the bottom of the tree, so that we can have a focus, so a direct access to one node at the bottom of the tree. And if we do this, So if we apply this zipper to this data structure, we can get an amortized constant time derivation, which makes the parsing algorithm linear time. We've proven the algorithm correct in Coq, and the proofs are also available on GitHub. And also, we've made this library available for you to use. It's also on GitHub. We've written a paper about this subject, and it's going to appear at PLDI this year. And in the meantime, it's available on arXiv. So thank you very much for your attention. I hope to see you soon at EPFL. In the meantime, don't hesitate to contact me by email. So thank you very much. Bye-bye.